Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 49, we will run about recurrent neural network and long short-term memory. So, the different concepts that will be covered in this particular lecture are on recurrent neural networks and sequential data, RNN architecture, RNN mathematical formulation, RNN limitations. Then we will move into long short-term memory, LSTM. Then we will look into LSTM architecture, and then finally we will explore univariate versus multivariate LSTM models, and then univariate versus multivariate LSTM models using Python. So, the recurrent neural network and sequential data, why we have already discussed this earlier. That means when we have sequential data like a time series data and all, the normal ANNs actually fail. So, we have to do something else, right? So, in that case, recurrent neural networks are actually utilized, and this RNNs are models designed for sequential and time dependent data, specifically for that. And why it is utilized? Because RNNs can remember past information through the hidden states. So, that is different from the standard ANNs. And these are used for language modeling, speech recognition, traffic forecasting, temporal pattern analysis, and so on. So, traditional neural networks, ANNs and CNNs, assume that all inputs are independent of each other, all the features are independent of each other, and order and context of data is important. But problem is order and in many real life problems, the order of the data or the context of the data, that becomes important. That means you cannot ignore how things are organized together, right? So, we do some amount of that. When we learn CNN, we actually try to explore some amount of features at different hierarchical, different levels in different convolution layers, right? So, that means we have tried to do that, but we need something beyond that, right? So, for example, word prediction in a sentence, stock price or traffic flow forecasting, weather sequence analysis, bus arrival prediction over time. So, that means if you don't know the earlier data or you don't know the context, it will be difficult to predict the future. So, some of the properties of ANN actually limit us from doing this kind of work or doing predictions for sequential data. For example, the first property is of course the independent and identically distributed assumption in ANN. So, the independence assumption is not valid for sequential data, of course, because the data points are not independent of each other. It is affected by, that means what would happen next is dependent on what is happening now. So, this is the one problem. Then the fixed input constraint is there. That means ANN require a fixed size input vector, whereas if I look into time series data or like GPS trajectory data, there is no fixed input. That also varies. Like image classification, we have fixed number of pixels, tabular data sets, we have fixed number of columns. But when I say time series data, depending on at which time point we are doing the analysis, that there is no fixed point. There is no fixed amount of features. The feature will change, right? So, this requires variable length inputs. So, that feature has to be introduced. And then lack of persistence is ANNs reset for every new input and do not retain memory between the steps. That means we train the model with a certain amounts of weights, and then we use back propagation to modify the weights and all. But that means every time we are resetting that, that is not that if that is the case for time series data, that cannot happen. So, ANNs, so that means in case of time series data, we need to retain some amount of memory of what happened in the earlier period, and then we move to the next period. So, in this case, that means the same architecture cannot work. For example, the clouds are in the dash dash. The ANN do not realize that either clouds and in will lead to sky. So, that means the clouds are in, of course, it would be sky, that we can say, but ANN will not understand that, right. So because it doesn't understand the context, it is taking cloud separately, in separately, all separately. It is not taking them in together, right? So, so in case of CNNs, while so ANN will absolutely fail. In case of CNN, we have done this 1D convolutions, of course, but these are used for sequence to understand the the way the features are related and so on. But these have limited capacity to link information in a time series or this kind of context. So again, so that means we have to look for newer architectures. This is where the RNN architecture comes in. So RNN architecture could be explained using this particular figure. So this is the unfolded, the folded version, and this is the unfolded version. Now RNN processes one element of a sequence at a time and carries forward a hidden state that acts like a memory. So RNN itself will process one element of a sequence at a time. That means it is not going to process the entire sequence together. It is taking one step at a time, right? So that means it is moving from one time point to another time point, and then it is looking into the transformation. But it is taking some amount of information into the next layer, right? Into the next, this you can say the next layer, right? So in or the next hidden layer. So in that case, some amount of information is carried, and that is carried via this particular loop that you see over here. So this is the folded view. It shows one recurrent unit. The loop arrow indicates feedback from the hidden state to itself. That means the hidden state is actually, that is being, transport that is being sent to the next hidden state, right? So that means we add a weight for that as well. That means it's not only the features or the output, but also the hidden state that also needs to be, conveyed. The recurrence is represented implicitly using this, and this where X is the input, H is the hidden state or memory, O is the output, and U is input to hidden weights. This one, U is the input to hidden weights, and W is the hidden to hidden recurrent weights, hidden to hidden recurrent weights. So that is something new that we are adding, and then V equal to hidden to output weights. So these are the things that we have to be considered. Now when I am unfolding it, that means now we are looking into a time series, right? So that means this is one step, this is one step, this is the next step, this is the first time period, this is the first time period, this is the previous time period, this is the next time period, and we are trying to predict, right, what would be the output in subsequent time periods. So over here we are now unfolding this particular folded view, and here you can see that input is xt minus 1, xt and xt plus 1. As you can see over here, hidden states are ht minus 1, ht and ht plus 1, and outputs are ot minus 1, ot and ot plus 1, right? So the same weights u, v, w are used for every time step. So now that we have u, v, and the third weight is set of weights is for the hidden state, of course, being being taken to the next step, and so we are using weights for that. But the same set of weights would be used for all these different time or this transformed points, right? All these different time series, right, or these instances. So this entire thing, now that we have represented it, now it's only the question of solving the weights. As we solve the weights, automatically the model is trained. So that means, and this is done via back propagation through time during the training. So now the question is, whenever we are defining a machine learning architecture, what we are doing is we are designing the architecture in such a way, we are designing the functions in such a way so that we arrive at that output classification or output, whatever the output is, we arrive at there. So that obviously there will be some activation function at the end to convert a score into an output. If these are all linear scores of the weights, that means each has got weight, we can fine tune the weight using back propagation and so on. So all these things needs to be done, and that means we will get, and when I fit this particular model to our data, the weights should be adjusted so that we get the outputs as we are observing, right? So that is how machine learning architectures work. So the architecture is designed here in such a way so that there is a memory component which is moving through, and we are deciding that. And now that we have decided that, we also have to introduce weights for determining how important is that component in the overall this knowledge transfer or signal transfer. So this is the RNN mathematical formulation. At every time step, the RNN processes the current input together with the hidden state from the previous step, combines this information and updates the hidden state accordingly. And the same hidden layer computation is applied repeatedly at each time step, where the information produced in one step is passed forward through the hidden state to influence the next step. So that's why we call it a recurrent neural network. So recurrent because we are doing it again and again, and we are using the same weights. So this is HT and XT. XT is the input at time t, HT is the hidden state at time t, and YT of course is the the prediction that we are getting, right. So HT minus 1 is the previous hidden state. So we are putting weights to it that. So WH is the hidden to hidden recurrent weight matrix. Then XT is of course the input. So we are giving a weight input to hidden weight matrix that has to be given, and hidden layer weight matrix. So that means we have the input layer. Suppose there are input layers x1, x2, x3, then there is the hidden layer, right. So for each of this we have to generate the weightage, right. So the weight matrix has to be calculated, it has to be determined. Then WH, so this is the first one, and then this beta H is the this BH is this bias that we are also introducing. Then YT, then what we are doing is, then BY is the bias, BY and BH are the bias terms over here, and F is the activation function, which is usually tan H or ReLU, and this we are taking an activation function of this one, and G is the output activation, that is depending on the task, and we can detect the output class, which is YT. So that means this is two activation functions are being utilized over here. So this is for classification task, we are doing this particular function, this output activation, where this is the transformation activation, that is this is F that is used, which is either ReLU or tan H. Now once this is the structure of the model, the mathematical formulation. Now of course we have to do the we have to train the model, right, based on the data that we are feeding it, and then we do it through back propagation through time BPTT, and the network is unfolded over multiple time steps. So that means we go back. So the network has to be, in this way we have to frame the network, and then for each of these values we have to find the W values, and so loss at outputs are computed. So this errors are propagated backwards through all time steps, and shared weights are updated, and the total loss is, the loss function is actually computed from the total loss. So this is total loss is the sum of losses across all the time steps. So t equal to 1 to t. So that means again the losses across each of the time step is actually considered, and then only we can determine the weights which would be common for all the different time steps as well. So RNAs, of course this is a way to get to carry some of the memory to the the next step using this hidden layer and all, and giving weights to it, but RNN has got several limitations. So there are difficulty in learning long term dependencies. So that means it's only a short term dependency, you are only learning about one, the previous layers information is coming. Then vanishing gradient problem is there, we already know what is a vanishing and exploding gradient problem, and slow sequential training is this problem is there, and memory of earlier input is actually limited. So the vanishing gradient problem actually tells us that as the network gets deeper, that means we have longer sequences, time series, the derivatives become smaller and smaller, right, because it would be a series of activation functions that we are taking. So because we are using activation functions like tan H or sigmoid, and these are all multiplied together during backpropagation through time, like we have discussed earlier, and this results in very, very small gradients, right. So the gradient exponentially shrinks to 0, and that is the model cannot link information that is far apart. That means it cannot move to the initial layers, right. So it becomes kind of shallow. So that is one of the problems that we face. The other is of course the exploding gradient problem. So if the weights initially are given large, the gradient grows exponentially through backpropagation, and this leads to massive weight updates, causing models to crash or produce NaN values, right. So sometimes we do gradient clipping, that means we cap the gradient at a maximum value. So beyond that we will not accept those particular connections or neurons. So this is sometimes done to avoid this, and then we also have unidirectional constraints. So standard RNNs can only see the past. However, future context is also sometimes required, which is missing in this particular RNN. So of course, to overcome this, there are advanced recurrent architectures such as LSTM and GNU to overcome these problems of this gradient and so on. And particularly this vanishing gradient problem is the one which we are trying to, which is solved via this long short-term memory LSTM, and then gated recurrent unit is a more simpler version of something similar. So we will discuss the long short-term memory architecture as well. So LSTM is a special type of RNN that can preserve information for longer duration using gated memory cells. So this is a new concept that we are considering. This is designed by Hochreiter and Schmidt-Huber to overcome the short-term memory limitations by allowing information to persist over much longer period. So instead of just one simple period, LSTM was designed to resolve the vanishing gradient problem in the first place. And unlike traditional feed-forward networks, LSTM processes entire sequence of data rather than individual data points. So this is where the entire sequence is studied together. So LSTM decides what to forget and what new information to store and what to output. So this is where that gates comes in. So this is done via cell state, hidden state, forget gate, input gate and output gate, right? So cell state is the status of that particular cell, whereas the hidden state is the intermediate layers. The forget gate, input gate and output gate are new ways to propagate the information to between the different layers. The gating system of LSTM is designed to overcome the vanishing gradient problem by controlling the flow of gradients during back propagation. The gates use the sigmoid function and the hyperbolic tangent function tan h to achieve this, and each gate in the LSTM can either add or remove information from the cell state, finally tuning the system to handle long-term dependencies effectively. So we will see how this architecture works over here. So in this particular image, you can see this is the forget gate, this is the input gate, and this is the output gate. We are starting with CT minus CT, which is cell memory. So what we remember, and this is for t minus 1 period, HT minus 1 is the hidden state of t minus 1 period, and x is the element, this input vector that we are putting inside, right? So x over here indicates element wise multiplication, plus indicates addition, and we are using sigma for sigmoid activation and tan h for hyperbolic tangent multiplication. So what is happening over here is the LSTM cell processes information at time step using current input, which is xt, previous hidden state ht minus 1, and previous cell memory ct minus 1. So this cell memory is something which we are now we are considering in LSTM. So it at the output, so finally it produces a new cell memory which is CT and a new hidden state HT after the processing is completed. So the role of forget gate over here is to decide which information from the previous memory should be discarded and which should be accepted. So we are getting this this input HT minus 1 and XT, and we are running the sigmoid function over this particular this particular matrix, this particular set of information, and then we are what we are getting is the sigmoid function output values eventually either it is 0 or 1. So this actually helps us to decide should I keep the information or forget about it, right? So if the value is 1, we will keep it. If the value is 0, we will forget it, right? So this FT value is either 0 and 1. So forget gate multiplies the previous cell state, that is CT minus 1 with FT, and if it is 0, that means it is nothing remains, but past information is discarded. But if it is 1, then the past information is carried over. So this actually determines which past information should remain in the model and which should be discarded. So the input, next comes the input gate, which determines what new information should be added to the memory. That means this process is also generating new memory, right? So that means it is going to create CT. Okay. So this input gate decision IT, similar as forget this decision ft. It is given by again sigmoid of wi ht minus 1 x1 xt plus bi. This decides how much new information to store. This is standard, this whenever we have got different hidden layers and all these things, we have to multiply the weights with the different connections and all, and that actually is being represented over here. So this is the equations, that weight equations. And then the candidate memory CT is equal to, this is where we run the tanh function, and it runs on, and we are using this WC over here. This is a new set of weights, and this ht minus 1 xt is the the matrix that it would be processed along beta. This beta c is the bias that we are adding to it, and this generates potential new memory content, and the memory update becomes, the new cell state becomes CT equal to ft into CT minus 1 plus IT into CT. So if we are retaining the memory, then we will again multiply it with ft, the previous memory, plus the current memory is what we are generating over here. So part of the old memory is retained and the new information is also added, and that becomes the new memory. The output gate controls what information will be sent to the next hidden state, and this OT is equal to sigma of W0. So this is the new set of weights again. So this is computed first, and then hidden state HT equal to OT into tan H of CT is computed, and this determines what information becomes the output of the LSTM cells. So this actually happens for each of this, for every step. So this is, we decide, should I retain some of the memory, should I discard some of the memory, what would become the new hidden state, what would be the new cell state, and then with one input xt, then this actually determines that what would go to the next step, and eventually we have to find the output as well. So in case LSTM could be univariate also and multivariate both. So in case we have got features or inputs, these are independent variables or past observation used by the model to learn patterns and predict the future. Target output is, this is the dependent variable that the model is attempting to forecast. So over in this case, in univariate LSTM, you see this is variable 1 and this is the target variable. So there is basically a single feature input. The input consists of only one variable observed over a chronological sequence. Feature and target variable is basically the same, and the architecture is designed to capture internal transition patterns, trends and seasonality within that specific variable alone. And so this is where like stock prices change and so on. So this is from between two steps, what are the changes happening of the same variable that is being stored. Whereas in case of multivariate LSTM, you can see that we have got several variables and then there is a target variable, and this actually is changing over time. So there is, the model takes multiple independent variables as input at each time step, and the target variable is dependent on the complex interaction between these multiple input features. And coming to the RNN modeling steps, or you can say even for LSTM, the same modeling steps will follow. We collect sequential time series data, pre-process and arrange into sequences. So that means the sequences has to be first framed, and then define input window and target, and then build the RNN LSTM or GRU model, whichever you want. Train the this particular train using this back propagation with time, then evaluate using suitable matrices, and use model for prediction or classification. So this is a standard RNN modeling steps. Now coming to an example, what we are doing over here is we are having a data set where for each date and time and every hour, date and time includes both date as well as the time of the day as well, and then for every hour, that is 17th hour, 18th hour, 19th hour, and the day of the week, which day of the week it is, day of the month it is, which is it a weekend or not, what is, and we are getting passenger counts at a bus stop, right? So that means at a bus stop, the number of passengers that would be waiting at different hours would be different, of course, but it would be also different during different days of the week. It will be different during different months, and if it's a weekend, again it is different, right? So the passenger count varies as per this particular time series. So in this particular model, we are going to train a model which will understand this, and using and then you understand this particular sequence, and then then it can also start predicting. The trained model would be able to predict what would be the passenger count in a new time period. So we are importing TensorFlow as TF, importing pandas as PD, NumPy as NP. We are importing mean max scalar. This is for scaling. This is we are importing from TensorFlow sequential. We have already seen this earlier. Then we are also from TensorFlow keras.layers importing LSTM, dense and dropout from sklearn. So this is for the LSTM model. Then from sklearn.preprocessing import label encoders. Then we are also from TensorFlow.keras.callbacks we are importing early stopping. So this actually stops the training of the model if we are not finding any improvement in the validation scores and so on. So we are also importing matplotlib for some nice plotting that we will do for the training as well as the predicted data. So we are reading this file metro.csv. We are printing the data.tail. We are printing the last 3 rows of the data, and so this is where the last rows of the data is being printed. Last few rows over here. Then data.info actually is giving this particular information, and then drop data date time, make sure data is in the sequence of time step. So that is what we are doing over here, and then that means we are dropping this date time, but we are making sure the sequence is there, and then we are doing the encoding day of the week, hour, month. So is it weekend? So these all are encoded, and then we are doing the normalization, converting everything into this zeros and ones within the range of between 0 to 1, and then once we are transforming the data, then we can also print the data, and you can see that this is the transformed data after all this scaling is done. And then we create that sequence, because any LSTM model will require a sequence. So that is first being created, and sequence length over here is 112, representing 16 active service hours over 7-day period. So every 7 days we are training the model. This explicitly tells the LSTM to look at the past 112s of data to predict passengers volume for the 113th hour. So the LSTM model architecture is we have a stacked LSTM structure. Dropout layer is introduced to reduce overfitting. Activation function used is ReLU, and we can tune the hyperparameters to find the best possible combination of hyperparameters. We can stop training the model if validation loss stops improving, and if there is no improvement over a period of 15 epochs. So first we are splitting the data into 80% of the data of the sequence is kept separate, and the remaining 20% of the data is used for testing. The first 80% is used for training. Then we are using a random seed as well to get the same result every turn. So we are using a fixed seed, and then earlier we were doing 42, here we are giving 0, and then this we are building the LSTM model over here. These are the sequential steps of the model. This LSTM 64 layer extends complex temporal patterns, return sequence equal to true, to pass the entire sequence of hidden states to the next layer, and maintaining the time and maintaining the timeline. So we are giving the dropout value as 0.2, which says that layers randomly deactivated 20% of the neurons during each training step. This acts as a severe penalty against overfitting, forcing the network to generalize rather than memorize the training data. And then dense is 1, which means that the layer condenses the complex LSTM logic into a single continuous numerical output, that is the predicted passenger count for the next hour. The model is compiled using mean squared error and the Adam optimizer. And we have introduced early stopping, that is the callback. The callback acts as an automated safety mechanism if validation loss fails to improve in 15 consecutive epochs, where patient's value is given as 15. So this is for early stopping, and then training halts immediately, and the model restores the best way to prevent overfitting. So that is what we are doing. So here we are now training the model over here, and X train, Y train epochs is given as 100, batch size is given as 16, validation split is 0.2. callback is introduced, verbose is 1 means we can see the steps in the model. So, now we are plotting the results. Once we have done the tested the model, now we can predict, right. So, we are directly predicting the values. So, and then we are creating the plot for it. So, you can see the plot actual versus predicted values. So, the blue ones are the actual values and the saffron ones are the predicted values. So, we see that it is mostly matched, and we can, using the scalar matrix for accuracy and all these things, we can also print out those values as we have done earlier. I am not explaining that in detail again. So, the within accuracy matrix provides a practical real world assessment calculating the exact percentage of predictions that fail within a strictly acceptable engineering tolerance of plus minus 3 passengers. So, that is what is being introduced over here, and that means the model evaluation matrix says the mean absolute error as 1.25. This is being printed over here. Root mean squared error is 1.61, R square value is 0.74, accuracy within plus minus 3 is 94.16%, normalized accuracy is 90%. So, this is the overall trained model and then the predictions that we have done. Now, this part of the code actually help us in forecasting the forecasting for the future, right, forecasting the next 16 hours. So, the model predicts the first hour, appends the prediction to the end of the sequence, drops the oldest hour and predicts again. So, that means it is a rolling prediction, and it is a auto regressive forecast, means we forecast one value, then we again utilize the entire sequence including the forecast value, the predict for the next. So, that is done over here, and we are using we are saving those values in using loops and all, and then we can also print those values as well. And then this inverse transformation is the raw mathematical prediction still, which is bounded by 0 and 1. That is how the model predicts, are passed through the scalar inverse underscore transform to convert them back into interpretable real world passenger counts. So, because we have already scaled the data and we are using trend test scale data and we are predicting based on that. So, that of course has to be reversed and we have to get back to actual passenger counts. So, that is what is being done over here. And finally, we can plot the last 7 days plus the forecast of the new 7 days, and then and we are forecasting for the next day. The final MATLAB line graphs stitches the actual data from the last 7 days, range sequence using this function, and then seamlessly into 16-hour predictive forecast, and that is where we are using this the range values to predict the forecast for the future as well. And this is the Lstm prediction graph that you can see over here. So, this is the hour index, negative equal to past, positive equal to future, right. So, the model clearly captures the cyclical nature of metro passenger data. The predicted lines strongly mirrors the rhythmic peaks and valleys of the actual data, proving the Lstm successfully learned the underlying daily and hourly usage patterns. So, this is how we can build a time series model using Lstm. So, these are some of the references you can use. And to conclude, recurrent neural networks model sequential data by using hidden state memory, while Lstm networks overcome the limitations of basic RNNs and enable effective learning of long-term temporal patterns. Thank you.